Hello, everybody, and welcome to this webinar on the ElectricalOM's functionality for PV. Hopefully, I'm going to keep this introduction relatively short. Then I'm going to hand off to Pam Boss, who's going to be doing the majority of the live demonstration of what's going on in terms of what we have here for the PV. So, pushing forward. Webinar's focus is all going to be around the design considerations for PV systems, particularly in relation to cables and protected devices and the various elements that are going to affect us design in doing those things. Where we have various warnings, we're also going to show different types of warnings that we've added into the system in relation to those going through. As always, the real focus around these sorts of things will be all about how we can take advantage of ElectricalOM's environment, how we can use its calculation engine, and how we're using that to provide information in detail for you about the systems that you design in there. And then obviously just highlighting, you know, we're trying to produce compliance within the system by referring back to various regulations and details within the likes of BS 7671, so on and so forth. We have got various other developments going on with this. So some of the things that you will see today aren't in the current official release. That will be coming very shortly. But also in the future, after that, we are further developing things around the PV. So looking at enhanced inverter settings to do with identifying power factors, other harmonic energy efficiency within systems, streamlining the need between BES systems so we can combine the PV and energy storage elements so it's more interactive in the way they behave in the software. Also, looking at particularly certification reporting. There is no real proper certification reporting system which has been fully utilized anywhere at the moment. So we are trying to pull information and details together on the best way that we can produce various types of certification reports for those who wish to do that within our environment as well. And hopefully we'll be doing more webinars again this year as we move through the year. I know we've got one or two ideas, things planned that we're going to be doing that throughout the year. So obviously watch the space on LinkedIn and the magazines and things that we send out in relation to what we've got going on. Feel free as we go through to ask any questions on the Q&A. Some of the answers I might do during the Q&A, others we might do towards the end if there's time. We are going to try and keep this into the hour, so we'll try and get through as much there, because there is a lot to show and a lot to talk about today in terms of what goes on within the PV environment here. And otherwise, please enjoy as it goes through. So I'm going to hand off now to Pam Boss, who's going to take over and show you some of the stuff directly in our environment. Thank you.
Thank you, Spencer. Allow me to share my screen. I hope you can see all my screen. Good evening, everyone. Thank you for joining our live webinar. Before we begin with our live demonstration of the new features and functionalities we made available in ElectricalOM, specifically for PV sizing, I'd like to quickly go through the topics that we will cover today. In particular, we will demonstrate how we can apply sections 712 calculations and checks in order to properly size and protect PV strings, PV string cables, and subarray cables. You can see from my screen all the calculations and checks that we will apply. Moving on, as you can see from the document I'm sharing, we will be using specific manufacturers' data. In particular, as you can see, we will be using a 10 kilowatt string inverter with optimizers, of course. And the modules that we'll be using will be 500 watt monocrystalline modules. And lastly, you can see some of the system configurations that we will cover shortly after. So we have a lot to cover. So let's move on to ElectricalOM to begin with our live demonstration. Okay. So as you can see from my screen, we are in the schematic area of ElectricalOM. We have a pre-configured three-phase electrical installation here, specifically for domestic use. We have the cutout fuse of the DNO, the main switch, and a main distribution board. So we'll be using this schematic to add on our PV inverters and strings for our live demonstration today. So to begin with our project example, I'm going to enable the schematic here. We'll be modeling a PV string inverter, a normal PV string inverter, and an inverter with power optimizers. To begin our example, I'm going to right-click on the main distribution board and add a three-phase inverter. As you can see, automatically the software has added an upstream protection and a cable at the AC side of the inverter. So now we're going to adjust the settings of the inverter and size the AC side of the inverter. So from here, we can access the settings of the inverter, and using those manufacturers' data sheets I showed you earlier on, I'm going to specify the settings of the inverter here. So for the maximum short circuit current at the input of the inverter, we're going to define it at 55.7 amps. The maximum voltage will be up to 1000 volts. The minimum voltage will change it to 200 volts. And the peak PV power will be 15 kilowatt, since we are using a 10 kilowatt inverter. In addition, we are able to specify the maximum AC current of the inverter in case the manufacturer provides this information to us. So for the moment, we are going to leave it as it is, and I'm going to apply the changes. Also from here, we are going to define the nominal rating of the inverter, 10 kilowatts. And as we can see automatically, we can see some warnings coming up, specifically due to the design current of the inverter. So we need to add an appropriate protection and size our cables accordingly. So from the protective devices tab, I'm going to add circuit protection by accessing the protective devices library. I'm going to use an MCB type C 10 KA for its breaking capacity, and I'm going to select a 20 amp device. In addition, I will adjust the number of poles to be a 4-pole device and apply the changes. Also, from the phase and neutral conductor tab, I will quickly select an XLPE armor cable for the supply of the inverter, for the AC side of the inverter. And I'm going to leave the installation method as it is. In this case, we can see that a 2.5 square millimeter cable is able to withstand the design current, but for best design practices, we're going to increase the size of the cable to 6 square millimeters and apply the changes. All the critical warnings at the bottom, as you can see, disappeared. Before we exit the circuit editor, I'm going back to the protective devices tab. I'm going to add lastly an S-PIN-DIN device, a T2 device, and adjust the continuous operating voltage of the device to 440 volts. I'm going to also change the conductor sizes here to match the main conductor of the PV inverter. And also I'm going to define where this SPND will be located before or after the incomer device. So, in addition, I'm going to select a circuit breaker for the SPND. And for the incomer device, we can define it here. You see the software automatically provides an RCD protection for the inverter. And also the software has selected for us a type B device. According to the manufacturer's datasheet, we may use a type B device or change it to type A if it's not necessary. Also, I'm going to change the rating of the device to be 100 milliamp instant device, 40 amp device rating, and disconnect the isolator since we will be using an RCCB device that provides switching and disconnection for the AC inverter. So I'm going to apply the changes and return back to the schematic area. This is so far what we have created. And to carry on our design, we will be adding some strings connected to our inverter. There are several ways we can model that. The proper way is to add the number of MPPT inputs to the inverter. So we're going to model that using junction box. This junction box will be named MPPT1. I'm not going to use the conductor for this junction box since will be used as the main input to the inverter. And to improve our schematic, I'm going to use the schematic functions to force to extension layout the component here. Okay, also I'm going to move the description towards the center of this component. So now we added one MPPT input to our inverter. I'm going to add several strings on this inverter. The only component that is allowed to be connected is a PV string, as you can see. And again, to specify the characteristics of our PV modules, we need to double click on this item here. And as you can see, again, using the manufacturer's data sheets I showed you earlier on, we're going to define the characteristics of our module. So our PV modules will be 500 watts. The short circuit current at standard test conditions will be 14.17 amps. In addition, we've been defining the maximum power current of our PV modules at 13.59 amps. And the module max overcurrent protective device that can be used is 25 amps, meaning that if we exceed this rating, we are not protective our modules because we are exceeding the thermal limits of our modules. Additionally, for the open circuit voltage, we are going to define it at 44.21 volts. And for the operating maximum power voltage, we'll set it to 36.79. So now we can see that we are getting a voltage drop warning because we haven't added any PV modules. By default, we are using only one. So I'm going to increase the number of modules from here. I'm going to set it to 10. And as I increase it, you can see the total kilowatt of the string. I'm going to set it to 10, as I said, apply the changes. Additionally, we are getting an important warning related to the DC to AC ratio for our inverter. We are only utilizing half the capacity of our inverter, so we know that we can add an additional string. Return back to the schematic area, and we can quickly copy and paste to replicate this PV string. And as you can see now, we quickly managed to model a simple domestic PV installation with two PV strings connected in parallel to the same maximum power point input of our inverter. So now I'm going to quickly copy and paste this. I'm going to show you what happens if I increase the number of PV strings. If I set it to 3, now, as you can see, we are getting several warnings from the warning area at the bottom. We can access any of these PV strings to find out what is going on. And from here, we can see the calculation checks that are taking place in order to help us properly size our PV systems. In particular, because we have 3 parallel PV strings connected together, due to the reverse currents that may occur from any of the other strings, we may exceed the thermal limits of any of these strings, as you can see here. And to check that, we are using the mod max, which is 25 times 1.35. So in this case, this gives us 33.75 amps. And to check that, we are using the number of strings minus 1 times the short circuit max value, which is 14.17 times 1.25, to see if we are able to withstand these fault current levels or not. In this case, as you can see, our PV modules cannot withstand these fault current levels. Either we need to add a circuit protection, decrease the number of strings, or change our modules with higher mod max capabilities. If I change the mod max value, let's say just for the sake of this example, to 40 amps, we can see that the warning disappears. But in most of the cases, you will find PV modules at 25 amps for the mod max characteristics. I will leave this warning as it is now. I want to show you a couple of other things. Let's move on back to our string inverter, and we're going to slightly change the settings of our inverter now. We're going to use optimizers. So I'm enabling the checkbox here for the power optimizers. We can define the fixed voltage for our strings now, since we're using power optimizers. We can define the characteristics of our optimizers here. I'm going to leave it as it is. I'm not going to apply any changes there. And also I'm going to enable this checkbox to make the optimizer symbol available in our schematic. I'm going to apply the change and return back to the schematic area. So as you can see, close to our PV modules, we can see that we have added some optimizers, and some of the warnings from the warning area disappeared now. So let's go back to any of these PV modules to see what is going on here. Because the optimizer symbol appears here now, from here we are able also to adjust the settings of our optimizers. The same holds for changing these settings from the inverter area as well. Because we are using optimizers, due to their current limiting capabilities and the reverse current blocking capabilities, we don't need to apply the mod max calculation checks we have done earlier on. And as you can see, the numbers here have changed. Now the I short circuit max is set to 18.75, whereas earlier on was slightly lower. And the reason for that is because we are using the maximum output short circuit current of the optimizers, which is set to 15 amps. 15 times 1.25, we are getting 18.75. However, because we have optimizers, we don't allow reverse currents to flow through towards our modules, so there is no need to apply the mode max calculation checks. But for our cable sizing, for our cable string sizing, we need to apply these calculation checks to make sure that the current carrying capacity of our cable is adequate to withstand any reverse currents that may occur at the secondary side of our optimizers. So in this case, we can see that a 6 square millimeter cable is adequate to withstand up to 57 amps. So there is no any warning here related to the fault current levels. However, because we are exceeding our inverter's characteristics, we are getting an important warning towards the bottom. So in this case, if we go back to our inverter and see from here, the maximum connected short circuit current is higher, is lower based on what we have. So if I quickly increase that, just for the sake of this example, we can see that this warning goes away. Okay. And the inverter is slightly oversized. The DC to AC ratio is 1.5, which is acceptable based on the industry standards, as you can see here. Okay, now we have managed to cover two simple examples, one string inverter and one string inverter with optimizers. Let's move on now to more complex designs, to my pre-configured design here. So for this example, we are going to show how we can connect multiple inputs to our DC combiners, and how we can use the calculations and checks to further protect our PV strings and PV string cables. So now we have our string inverter again, without any optimizers enabled. We're going to add again the inputs, the maximum power point inputs of our inverter. Very quickly, I'm going to name that to an MPPT1 and check the use conductor and improve the schematic like so. And from my previous examples, I'm going to copy this junction box with these two PV strings on this MPPT1. And in this case, I'm going to rename this component here. I'm going to rename it to be combiner DC box 1, or we can keep it for short, DC box 1. And also I'm going to enable the use conductor in this case. As we can see, we're not satisfying the minimum IZ characteristics here. So I'm going to increase the cross-section area of the cable to at least 4 square millimeters is adequate. I'm going to change it to 6 and change the length of the cable to 15 meters. Apply the changes. Still, the cable satisfies the requirements here, but let's see what happens if I further increase the number of PV strings. Let's add 4 PV strings. Again, we are getting similar warnings we used to get earlier on. As you can see, due to the increase of short circuit currents, the cable is not adequate now to withstand these current levels. So we know that we have to use protective device. So from here, I'm going to use an incoming protection. And immediately, we perform this calculation check here to make sure that any reverse currents that may occur between our strings will not damage our PV modules, because at this point, if I apply the changes and return back to my schematic, we can see that we have only one main protective device that protects any of the downstream strings. So in this case, although we satisfy the requirements for the upstream cable, we are not protecting the downstream strings in case of any reverse currents between any of the strings. So let me return back here to try to play with the numbers to see how these checks are affected. I'm going to select at least, let's say, an ATM device, 2-pole device, apply the changes, and we can see that we are getting this minus value here because, again, the mod max characteristics of our PV modules are not high enough to satisfy the requirement of the number of parallel strings times the short circuit current of each of the strings. So if I go back to our strings and let's say put a high number here, let's say 150 amps, apply the change and replicate this change to the other PV strings, we can see that the warning related to the single protective device that protects the downstream strings disappeared, but now we have to deal with the current carrying capacity of our cable. We have to increase essentially the IT of our cable. So I'm going to change the cross-section area of our cable to 16 square millimeters and apply the change. And again, we can see that by applying these changes, we can satisfy this condition here. But we all know that 150 amp mod max characteristic for our PV modules is unrealistic. So I'm going to set it back to 25 amps. And again, we are getting these warnings here. Another way to deal with these warnings is to add power optimizers, of course. So I have to go back again to my solar PV inverter, enable the optimizers option, apply the changes. I'm not going to bother with the DC to AC ratio here. We know that we significantly exceed the capabilities of our inverter. Just for the sake of this example, we are going to omit that. And because now we have power optimizers connected to our modules, we can see that we are not performing the calculation checks for the single protective device that protects any of the downstream PV modules. And the reason for that is because, as we mentioned earlier on, when we are using power optimizers, we are not allowing any reverse currents in our strings. However, we have to properly size our PV string cables to satisfy the requirements of the minimum IZ here. The minimum IZ is based on our protective device here. If we go back to our strings, further we can see that the minimum IZ for our string cables is based on the number of parallel strings together. We have 4 parallel strings, and the way we are calculating this value is based on the number of parallel strings -1 times the short circuit current of each of the strings. Because although we are using optimizers, the optimizers are located towards the ends of our modules, and this cable here needs to be protected from any of the reverse currents that may occur. So that's the case we have to slightly oversize our PV string cables. And like so, I can copy and paste this to further increase the capacity of our system. As you can see here, to account for more complex designs. Moving on now, we're going to tackle the most complex system configuration, which includes arrays and subarrays. So to do that, I'm going to replicate this. So I'm going to move this down here. So in this case, I'm going to delete these connection boxes here. I'm going to leave one maximum power point input for our string inverter. To further improve my design, I'm going to use again the force extension layout, and I'm going to connect on it the downstream junction box to account for our main combiner. So I'm going to call this combiner box. Quickly, I'm going to size its cable to be 6 square millimeter. And I'm going to connect on the downstream of this several other junction boxes to account for the individual DC boxes that we may have on the downstream. So this area here characterizes our main array, and this area here characterizes our subarray. So we're going to have multiple subarrays, as you can get. I'm going to call this DC box 1. Okay. And we're going to quickly connect PV strings on it. And I'm going to replicate this DC box 1 several times, at least 3 times. So as you can see, this is a fairly complex system. We have 3 subarrays. Each subarray has 4 strings. In this case, we may experience reverse currents on the individual strings. 4 times 3 is 12, 12 minus 1 is 11, 11 times the short circuit max is the 4 current levels that we may experience, or any of these strings. Because although we are using PV optimizers, we don't see the calculation checks that are taking place without optimizers. So I'm going to quickly disable the option for the optimizers. I'm going to disregard these warnings related to the inverter settings. And as you can see here, we can see the calculations and checks that are taking place due to the increase in the reverse currents that may occur. In this case, we're getting 192.5 amps. So we have seen earlier on how we can deal with these kind of scenarios. For this case, though, we're going to concentrate on the subarray cables. So So by accessing any of these DC boxes here, we need to make sure that our subarray cable is able to withstand any of the reverse currents from the other subarray cables. So we have 3 subarray cables, and as we can see from the applied check here is the short circuit max value of each of the subarray times the number of subarrays minus 1. In this case, we are getting 140 amps. So because we don't use any cable protection, so to deal with this kind of problem, we are going to add protective devices to each of our subarrays at the incoming side of our subarrays. And again, by doing that, we are performing the checks for our strings for the reverse currents that may occur in case these strings are only protected by one protective device of the subarray. So quickly, I'm going to use a value of 80 amps. By the change, still we have to deal with the problem related to the PV strings. Very quickly, we can access any of these PV strings. And to deal with this problem, either we have to enable power optimizers to restrict any reverse currents in our PV modules, or we can enable circuit protection for each of these strings here. So I'm going to use a protective device here. And as we can see, the value of our protective device needs to be between 19.25 and 25 amps. 25 is the mod max, the maximum overcurrent protective device that we can use. And apart from this calculation check that we are performing here, we are applying this IEC 62548 standard calculation to make sure that the protective device that we'll be using is the correct one. So for this PV string, I'm going to select a 25 amp device. As you can see, this device satisfies our condition and apply the changes. We are getting a voltage drop warning because of the number of modules that we have. So I'm going to increase it to 10, apply the change, and adjust the minimum and adjust the cross-section area of our cable. I'm going to set it to 6 square millimeter and apply the change. So to quickly replicate that, I'm going to select save and update all PV properties. And I'm going to delete these 2 subarrays and replicate these again, so I don't have to define all these characteristics again from scratch. And as you can see here, we don't have any problem with the reverse currents related to the subarrays. And also if we move on to the strings, still we managed to satisfy any requirements related to the reverse currents since we are satisfying the mod max characteristics of our strings. However, we haven't sized properly our array cable here, so we need to increase the size of our cable to satisfy the requirement of the total short circuit max value of our array. In this case, we may use parallel cables, 25 square millimeters, and apply the change. And by applying all these quick changes, we can see that we managed to eliminate all the critical warnings that we had earlier on. So this is how you can tackle a fairly complex system by having arrays, subarrays, and multiple PV strings connected all in parallel together. So to recap, we managed to cover some simple PV designs with 2 parallel strings connected in one MPPT input of our inverter, parallel, 3 parallel strings connected to one MPPT input. We showcase how we can utilize power optimizers to restrict any reverse currents. Also, we showcase how we can have one main protective device for any of the downstream PV strings, and how we can mitigate any of the reverse currents using power optimizers or by adding circuit protection individually to each of our strings. And lastly, we showed how we can model a system with several subarrays. So all these PV designs, you may find them in small installations specifically for PV design, for domestic installations. And to show you how ElectricalOM can be used for fairly large utility scale systems, I have an already designed project here. This is a real world project where we have a 3 megawatt PV system connected to the medium voltage grid, and we have our own private substation that steps down the voltage to 800 volts. We have the main switchboard here with fuses, 160 amp fuses at 800 volts that supply our PV inverters. And from our PV inverters, we have our MPPT inputs to our strings. And all these systems together can supply electricity to the grid, as you can see. So thank you for your attention. Hopefully you found our live demonstration interesting and informative.